Thanks. Hi, I'm Danqi Chen from Stanford University. Today I will talk about our work on using neural networks for dependency parsing. Dependency parsing is likely to be crucial to many NLP applications, such as machine translation and information extraction. Besides accuracy, speed is also a very desired property in dependency parsing. So our final goal is both accurate and fast parsing. In this work, we propose a neural network-based dependency parser. I will give you a big picture of what we are doing. We compare our parser with several widely used dependency parsers on English Pantry Bank dataset. First, Mod Parser is a very popular greedy transition-based parser. It can get 89.9 of unlabeled attachment score, and it runs very fast. ZPAR is basically a re-implementation of Mod Parser with very rich features and using Bing search of size 64. You can see that Bing search can improve the parsing accuracy a lot, but also making the parsing much slower. Next, MST parser and turbo parser are two representative graph-based parsers. They tend to have higher scores, but they are also parsing quite slowly. Here is where we are. Our parser is also a greedy transition-based parser. Now we can get around 92% of accuracy, and our parser is running even faster than Mod Parser. We can parse 1,000 sentences per second for English. And we also believe that the Bing search, like the Mod Parser, Bing search can improve the accuracy of our parser, but also reduce the speed. But today we will only focus on greedy parsing and leave the Bing search to the future work. This outlines my talk, and I will begin with background and motivation. The class of greedy transition-based parsers tries to predict a transition sequence from the initial configuration to the terminal configuration, and the dependency graph will be completed during this process. A configuration is a stack, a buffer, and also some dependency arcs. A greedy parser aims to learn a classifier from the configuration to the transitions. Our parser employs the arc standard system, where there are three main types of transitions: left arc, right arc, and a shift. A left arc transition pops the second stack element and attaches to the first stack element. And a right arc transition pops the first stack element and attaches to the second. And a shift transition moves one element from the buffer to the stack. So our work is focusing on learning this classifier using neural networks. We will first examine the traditional approaches. So the traditional approaches usually extract several millions of binary and sparse features from this configuration based on some feature templates. A feature template is usually a combination of 1, 2, 3 elements from the configuration. Here are some typical features. In these features, we use Si to represent the ith stack element, and the Bi to represent the ith buffer element. In this example, S1 is good, S2 is has, and B1 is control. We also use W, T, and L to represent the word, parser tag, and dependency labels. We use like LCRC to represent the structure information like the leftmost child of an element. So what problems do these features have? We think there are three main problems. The first problem is that these features are clearly very sparse. This is actually a very common problem in many NLP applications because of the lexicalized features. But we think the situation is even worse in dependency parsing because the high-order interaction features plays a very important role in dependency parsing. Here we give a very simple feature studies. We found that After we exclude all the three-word combination features, we will get more than 5% loss in unlabeled attachment score. After we exclude all the lexicalized features, the accuracy will drop 7%. The second problem, we think, is that these feature templates are usually very incomplete. Even with expertise and manual handling, it's very difficult to include all the combinations of all the useful combinations. For example, if there is a long-distance dependency arc from the first stack element to the third buffer element, we can tell the classifier that we cannot do a right arc transition. But the combination of these two tokens are usually ignored in almost all the feature templates. The third problem, we think, that the generation of these indicator features are usually very expensive. It sounds simple that we only need to concatenate several strings and look them up in a big table containing millions of features, but usually it actually dominates the parsing time. So to tackle all these problems, our solution is to use neural networks. We try to learn a dense and compact feature representation, such as 200 dimensions, to completely replace the indicator features. So we are wondering how difficult it is to use a 200-dimensional feature to represent the configuration. We think the first challenge is how can we encode all the available information of the configuration. It includes words, parser tags, dependency labels, and also all the structure and position information. And the second, how can we model the high-order features in the dense representations? Okay, let's get started. So to construct the features and their interactions, we choose to use distributed representations as a starting point. Particularly, we represent each word as a d-dimensional dense vector. They are well known as word embeddings and have been proved very useful in many NLP applications recently. So in word embeddings, we expect that similar words should have closed vectors. So in this work, at the same time, we also represent the parse speech tags and the dependency labels as d-dimensional vectors. We call them parse speech and dependency embeddings. We think that these smaller discrete sets can also exhibit many semantical similarities. For example, in parse speech tags, the NNAs should be close to NN, and in the Stanford dependency labels, the numerical modifier noun should be close to the adjective modifier A mode. The second step is that we want to extract a set of useful tokens based on the positions. For example, if you consider to extract the first and second stack elements, the first buffer element, and also the leftmost and rightmost children of the stack elements, in this example, we can extract the words, parse speech, and dependency labels like this. We think that in this step, it's much cheaper if you want to include more elements other than the indicator feature combinations. Now, we already have the distributed representations, and we also have extract a set of useful tokens from the configuration. Now we feed the corresponding word, parse speech tag, and dependency embeddings into a feed-forward neural network. So the input layer is a concatenation of the embeddings of different types. Then we build a fully connected hidden layer about the input layer. Unlike the standard neural networks, we propose to use a cube activation function here. And then we add an output layer, which models the softmax probabilities from the hidden representations to the transitions. You might notice that we are using a completely new cube activation function. And we think that this cube function can contain the products of three things from different tokens, and it can better capture the interaction terms. And we will verify this point in our experiments. So in the training, we use a fixed oracle to generate training examples, and we use cross-entropy loss as the training objective. And all the errors will be backpropagated to all the embeddings. Moreover, we use pre-trained word vectors to initialize the word embeddings. And we use random initialization for the parse speech and dependency embeddings and other parameters. In the parsing process, we need to extract some tokens from the configuration and perform matrix multiplications to compute the hidden representations. In our parsing, we apply a pre-computation trick similar to the Delving 2014 work. That is, if we have seen the S1 equals to good many times in the training set, then we can pre-compute the matrix multiplications before parsing. Then the multiplications will be reduced to the additions in the final parsing process. And in the practice, we found it can run 8 to 10 times faster. Okay, now let's review the 3 problems I just mentioned. For the first problem, we propose the distributed representations, and we believe that they can capture the similarities between different objects. For the second problem, now we don't need to enumerate all the combinations, and we believe that the cube nonlinearity can learn the combinations automatically. For the third problem, instead of the string concatenation and the lookup in the big table, now we only need to do matrix operations, and the pre-computation trick can help us speed up. Now, I will present the experiments. We conduct experiments on the Chinese and English pantry bank data sets. We use 2 corner representations. We use 2 representations, the corner representation for both languages and the Stanford dependencies for the English data set. To generate parse speech tags, we retrain Stanford parse speech tagger for the English data set. And to follow previous work, we use Go tags for the Chinese dataset. In all our experiments, we use embedding size of 50, hidden size of 200, and we use mini-batch ADA graph for optimization with 0.5 dropout on the hidden layer. For the pre-trained word vectors, we use the Colbert and Weston 2011 embeddings for English, and use our trained word-to-vec embeddings for Chinese. And we also use a rich set of 18 tokens from the configuration. And you can see the details in our paper. We compare against 3 baselines. The first is our own implemented perception-based greedy parsers using both ArcStandard and ArcEg system. The second is mod parser with 2 algorithms. And the third is a graph-based parser MST parser. Here are our main results on unlabeled attachment scores. You can see that our parser works consistently better than the other parsers. Compared with the previous greedy parsers, our parser is at least 2% better in English and 1.2% in Chinese. And we have a similar performance or even better performance on labeled attachment scores. In terms of parsing speed, you can see that our parser is like twice faster than mod parser, and it's more than 50 times faster than MST parser and maybe other graph-based parsers. Next, we want to examine the effects of different components on our parser. The first thing is cube activation function. We compare our cube function with identity, sigmod, and tangent h. In this slide, you can see the cube function works consistently better than the other functions, and it's actually 0.8% to 1.2% better than the tangent h or sigmod. And the second thing is the pre-trained word vectors. And we have 0.7 gain in English data sets and 1.7% gain in Chinese. And we also claim that our parser is actually is still quite good even without the unsupervised information. And we want to examine the effects of the parse speech and dependency embeddings. And we found that the parse speech embeddings help a lot. We have 1.7 gain in English and more than 10% in Chinese. And we can also get slight gain from the dependency embeddings. And we think that the dependency embeddings are not that useful is because the dependency labels are generated during the greedy parsing process and might have some errors. Finally, we want to look at how these learned embeddings capture. So we plot the Tisney visualization of the word embeddings, and it clearly shows that these embeddings can capture some similarities. So this is parse speech embeddings. You can see that the verbs, the nouns, the adjectives, adverbs, and the punctuations are actually grouped together. We can also examine the dependency embeddings, and we can find similar things that, like the subjects, the noun modifiers, the preposition complements are also grouped together. So to sum up, in this work, we presented a state-of-the-art greedy parser using neural networks, and it has excellent accuracy and speed. We also introduced the parse speech tag and the dependency embeddings and the cube activation function and found that they are very useful. For the future work, we consider to incorporate the Bing search. We also considered the recent work of dynamic oracle. We will also try to explore the richer features such as the lemma, morph, and distance. And we will continue to explore the better representations for modeling the the word interactions. In the end, the most important thing is our code is available. We just released the new version of Stanford CoNLP. And now you can try the fast dependency parsing in our CoNLP pipeline with a new annotator that parse. You can also check out our full training and testing code at this website. That is all for my talk. Thanks.
Questions?
Thank you. It was an excellent talk. You said that the embedding the dependencies doesn't improve the precision. If you eliminate the dependency embeddings, would it speed up the time?
It might be, yeah. But yeah, so we have less number of the tokens. But actually, if we just add the dependencies to the embeddings to the word embeddings, it actually has slight gain.
Hi, very interesting talk. I just wanted to ask something about the nonlinearity you used. So standard sigmoidal or hyperbolic tangent activations can also be like considered. I mean, if you expand it as a power series, you can think of like an arbitrary order combination of input layers. But for some reason, I mean, yours works better. Do you have any comments on that? Like, is 3 a special number, or is it just a learnability problem of sigmoidal activation functions?
Actually, we have tried like the force power and found actually force power is actually worse than the cube. And we think that in the transition-based dependent parsing, the 3-word combination might be the most important. So we think that the cube can capture that product term.
Thanks.
Yeah, very interesting talk. Thanks.
Thank you.
I'm wondering if there are multiple orders of rules that can use the same dependency parse, or if it's always unique, and if it's not unique, if that gives any problems in the learning.
Sorry, I didn't get the question.
So I imagine that it could be that there are multiple sequence of rules that still yield the same dependency parse, and or if this is always unique. There are
You mean
always
multiple roots?
yeah, because you're applying the rules to, you're sequencing the rules to build a dependency parse, but is there always one unique set of rules that maps to one dependency parse, or is it like in translation there are multiple ways to build one dependency parse with different combinations of rules?
I suppose you mean that different, even for the same dependency parse result, you can have different paths to go to that result.
Oh, you mean different assistants or algorithms like ArcStandard, ArcEagle?
Is that
Different segmentation.
So my understanding is that for this type of method, transition-based, you can
Yeah.
actually, achieve output the same result, but through different transition path in your algorithm. So, does your method actually affect that result, or yeah?
I'm not sure if I understand correctly.
Okay.
So you are talking about that because our parser is a greedy parser, so after the classified fix, there is a unique path, and we consider to use Bing search.
So guys, probably you don't see that because it's just greedy. Yeah.
So if I understand correctly, the cube activation function corresponds to a combination of 3 words.
Yeah.
Have you tried mixing combination of 2 words, 3 words, or 4 words, like obtain a more complex model? Something like word n-grams. Usually you can use 2, 3, or 4 word n-grams for some tasks to improve performance.
Actually, I just mentioned that we have tried like the false power and found it actually works worse.
But have you tried to combine them?
We haven't tried that.
Maybe one final question.
If I understand correctly, you use 2 different methods to get the word embedding for English and Chinese.
Yes.
One is Word2Vec and the other is Cobalt and Western.
Yes.
I wonder what happened if both were on the same technique.
Actually, for the Colbert and the Western English embeddings, we found it works the best actually compared with Word2Vec vectors. But we actually do not have Chinese embeddings from the Colbert and Western, so we use Word2Vec.
Okay. Can I have another question? Okay, the last one. I wonder how you train how did you get the embeddings for the post tags and the dependencies?
I just use random initialization and the backpropagation.
Okay. You trained it with the system, right?
Yeah.
Yeah. Okay, thanks.
All right, let's thank the speaker again.
Thank you.